Now this is the time to discuss the Poisson distribution. We will be deriving a formula for this type of distribution using a simple example of a radioactive element. A radioactive element contains a large number of atoms, say n, and at random any of these atoms being radioactive emits some particle, maybe alpha, beta or gamma, we don't know. Let us just consider that it emits some particle, and we have placed a detector which, whenever the particle is detected by this device, we get a count on our display. This is how we can effectively count the number of particles or number of disintegrations performed by this radioactive sample. And we need to calculate the corresponding probability that n number of counts, suppose small n number of counts, are detected in a given time interval t. Before that, let us assign or define a value that, let us just say, the probability that only one particle is detected in a small, very small time interval delta t. Now we assume that there is a very short duration of time delta t, and we are considering of probability that only one particle is detected in this duration. Obviously, this probability is going to be proportional to delta t. That is, larger is this interval of time delta t, larger will be the probability that a particle is detected by the detector. So which is going to be equal to some mu times delta t. Note that mu is just a constant here, or the constant of proportionality, replacing this proportionality sign by the equal to sign. Let us introduce a standard notation for this as well. When we write as Pn of t, we are calculating the probability of detecting n counts during time t. So if we carry forward this notation in this case, this can be denoted as P of 1 delta t. So probability of getting one count, that is one particle, in a duration delta t. If this is the notation to be followed, P of n t plus delta t would be then just probability of getting n counts in time, a slightly larger time, t plus delta t. Now this particular event of P and t plus delta t can take place in two possible ways. Either we get n particles detected in time t, and the remaining, since there is no particle remaining, 0 particle is detected in time, in the next interval of time delta t. This is one possibility, or we can have it in this way as well, that n minus 1 particles get detected in time t, and the remaining one particle is detected in the remaining time interval delta t. Now this probability consists of a logical combination of these statements. These two statements connected by AND operator, these two statements are connected by AND operator, and the two square brackets are connected by OR operator. And we know from the logic or probability theories that AND indicates dot and OR indicates plus sign. So let us just introduce the symbols. P of n t plus delta t is then equal to n particles in time t is nothing but P of n t. 0 particle in delta t is P of 0 delta t. We are just following the notation developed by us. N minus 1 in t is P of n minus 1 t into 1 in t is P of 1 delta t. Now we should note as well that P of 1 delta t is mu times delta t, that is probability of getting one particle in delta t. Then probability of getting 0 particle in delta t is just 1 minus the other option, right? So if probability of getting heads is 1 by 2, just for an analogous example, let us take tossing of a coin. Probability of getting head is 1 by 2. What is the probability of getting tail? It is 1 minus the probability of getting head. In the similar manner, if the probability of detecting one particle is mu into delta t, then the probability of detecting no particle is 1 minus mu into delta t. So let us just substitute these two values here and write it as P and t into 1 minus mu delta t plus P n minus 1 t into mu delta t. Now this can be further simplified. This mu delta t can be taken common, of course, and this can always be simplified to write as Pn t plus delta t minus Pn t divided by delta t is equal to mu times Pn minus 1 t minus mu times Pn t, right? This is what we get as an intermediate step. Now we are going to make this time interval delta t infinitesimally small. So we are assuming here that delta t is now tending to 0. And we know by the definition of limit that in the limit delta t tending to 0, this quantity on the left hand side is nothing but the derivative. So this is just dpn t by dt. By the definition of derivative, the LHS is nothing but dp by dt. Mu can be taken common and we can write it as P of n minus 1 t minus P of n t. So we have with us a differential equation. Actually, this is not a single differential equation. This is a set of n differential equations, each corresponding to a given value of n. Of course, we need to solve all those equations but in principle that is not required. Let us just substitute n equal to 0, see what happens. Then substitute n equal to 1, see what happens. Substitute n equal to 2, see what happens. And then we are going to generalize the result for any value of n. So for n equal to 0, this becomes very much simple, because then we get dp0 by dt is equal to mu times p0t. So n, instead of n we are going to substitute 0, so we get a 0 here, a 0 here, and 0 minus 1 is minus 1. P of minus 1 has no meaning. Why? Because detection of minus 1 particles has no physical meaning in itself. So this is not defined, so this is 0. So what remains is mu times p0t, of course with a minus sign. This is a simple differential equation. It has a solution of this type, p0 equal to e raised to minus mu t. So yes, the first easier part is done for n equal to 0. Now similarly we can keep on doing. So for n equal to 2 we would have n equal to 1 we would have n dp1 by dt equal to mu p0t minus p1t. We already have an expression for p0 which can be substituted back here, and then we need to solve this equation as well, which gives us, of course we are not going to solve it in detail, mu times t e raised to minus mu t. This can be done n number of times. If it is done, we see that p of n is just equal, of course p of n is a function of t, p of n is just equal to mu t raised to n upon n factorial e raised to minus mu t. This is what we get after generalizing the result by solving differential equations. Now we are interested in a unit time interval. So suppose we substitute t equal to 1, that is probability of getting n counts in unit time. So we get p of n equal to, so t is replaced by 1. So p of n is now the probability of getting n counts detected per unit time is just mu raised to n upon n factorial e raised to minus mu. This particular equation which we have got is called as Poisson equation or Poisson distribution. We will take an example to understand this further. Consider that there is a radioactive source which emits particles, as we have already discussed, and there is a detector which detects 1800 counts in 10 hours. So 10 hours is nothing but 600 minutes. So let us calculate the mean value mu. Of course, we can prove that this mu appearing here in this formula, which was introduced by us by saying that it is just a constant of proportionality, we can always prove that this mu comes out to be the mean value of this particular distribution. So mu in this case is 1800 counts divided by 10 hours into 60 minutes. So we are just going to convert this into counts per minute. So this is just 6 3s are 18. So 3 counts per minute is the average value. So we can ask a number of questions. So during how many 1 minute intervals? So note that since we have been asked about the 1 minute intervals, we are asked to find out the probability per unit time. So we are going to apply this formula. So during how many 1 minute intervals we get to detect no particle, that is n equal to 0, one particle, that is n equal to 1. Of course, this can be done for further values n equal to 2, n equal to 3 and so on. We note that Pn, since we are discussing about unit time, it is just Pn equal to mu raised to n upon n factorial e raised to minus mu. So P0 would be mu raised to 0, that is 3 raised to 0 upon 0 factorial e raised to minus 3, right? Mu is 3 and n is 0. So this can be solved to get a value equal to 0.15. Similarly, we can do for P1. P1 can be done as 3 raised to 1 upon 1 factorial e raised to minus 3, which is just 0.225. Note that the probability has increased now. The probability of detecting 1 particle unit time is larger than probability of detecting 0 particles unit time. Similarly, we can find out P2, which is again 0.225, and then P3 can also be found out using the same logic by writing it at 3 raised to 3 upon 3 factorial upon e raised to minus 3. It comes out to be equal to 0.70. Now we note that the probability of was maximum here, then it again dropped. So what is happening? We should note that this is a distribution and the mean value is determined in such a way that the mean value always corresponds to the maximum probability. And note that mean value here is P. Of course, there is a slight correction. Even P0 is 0.15. Sorry, P0 is 0.05. P1 is 0.15. P2 is 0.225, that is correct. P3 is again 0.225. P4 is but a slightly smaller value, 0.70, right? So we can see it on a graph. We can always plot it on a graph. P0, so this is x and this is P or f of x. For x equal to 0, P has some smaller value. For x equal to 1, it has some larger value. X equal to 2, it has some further larger value. X equal to 3, it has the same value 225. X equal to 4, the value drops again. So this is a typical distribution which we are getting, and we see that the distribution or the probability for this distribution has maximum value for n equal to 3, which is also the mean value of this distribution as well. So this example makes it clear how the Poisson distribution is used to study such type of problems. Thank you.